All right, let's consider this example. So here we're asked to find the magnitude of the resultant force acting on this dam due to hydrostatic pressure. So 10 meters wide is um, the depth of this right into the page, and we see that it has this radius of 3 meters, and we're just using water. So we can break this up again into vertical and horizontal forces. And if we think about, because this goes all the way up to 0, we know we have no pressure here, right? And what do we really have? Of course, these forces are getting bigger as we go down, and they're changing direction because we know that they're going to be acting right perpendicular to the surface. So it's going to look something like this, right? Which looks a little scary at first. But we can break this up into vertical and horizontal forces to see what this actually is. So let me draw this thing here, right? So we have, right, and maybe it's something like this, right? Anyway, but the idea is that you have this mass of water, right, that's kind of on top, pushing down. So that's going to represent the vertical component. And we know we're given that this is going to be 3 meters, this is going to be 3 meters, and this is going to be 10 meters. So our only goal right now is just to find the volume of water, right, that this thing has to support vertically. And then we'll use that to convert it into the resultant force, since pressure and the mass, right, are exactly the same. So we can see that the volume is going to basically be the volume of the square. So there's this square here, of course, times the depth into the board. And we can subtract out this stuff, right? And that will get us this area, and then we'll multiply that by 10. So that's the strategy. So let's go through that. So the volume for the square is going to be 3 meters, or sorry, the area for the squared, of course, is the 3 meters squared, minus the area for a semicircle or a quarter circle, and that would be in your equation sheet that you'll be given, pi times the radius squared divided by 4 in this case, right? Or the area. And all that times 10 meters. And so now we have a resultant force, right? Fry in the vertical direction just equal to this weight, right? Which is equal to rho g times v, now that we solve for v. Right, and this would be acting at the centroidal location in the x direction, but fortunately this question doesn't ask for that, but that's what you would do. You would go find where is the centroid, where's the x location of the centroid for this, right? The y location is irrelevant. Now on the horizontal side, what we have, we'll just draw this in 2D, is the vertical pressure gradient, right? And so it's the same as thinking of this thing again. So we start at 0 because the water goes all the way to the top, right? And so now we know the pressure here is equal to rho g times the depth, 3 meters. And now we can write the resultant force, right, as 1/2 base P times the height, 3 meters, times the depth, 10 meters, or sorry, the width into the board. We've just defined P, so now we know that the resultant force in the x direction is equal to 1/2 rho g, 3 meters again, squared, times 10 meters. So the resultant force, now you have two force vectors. You have a y component and an x component. So what's the resultant force magnitude? Which is due a vector sum, right? Frx squared plus Fry squared. And again, where this acts, this question doesn't ask for it, but this one, of course, would act a third of the way up from the bottom, right? So you would take the third of the way up here and then figure out where the x component for this stuff is, and that's where that total resultant force would be acting. Okay.